Hi, everybody. Thanks for joining us today to learn about large language model fine-tuning using Domino and NVIDIA NeMo. My name is Josh Mineroff. I am a director of solution architecture at Domino Data Lab. I'm going to allow John to introduce himself.
Hi, I'm John. I'm a senior product manager at Domino Data Lab.
So we have an agenda today. We're going to go through an introduction of what we're going to talk about. We're going to talk about the Gen AI challenge of actually taking a existing foundation model and tuning that to your specific use case, how you can go about doing that, how both Domino and NVIDIA help. Then we're going to go into a demo. John is going to run that demo, and then we're going to have some time at the end for Q&A. So first, I want to give you a high-level overview of Domino in 60 seconds. Domino is an MLOps platform that can run on-prem or in the cloud and allows you to do end-to-end development and publishing and monitoring of models that you want to build. We do that by providing four key things. We give you on-demand infrastructure, so you have self-serve access to the compute and tools that you want to use. We have comprehensive reproducibility built on 10 years of working with large enterprise customers. So this makes it easy to collaborate across teams working in different verticals or different geographies. We help accelerate and make more repeatable the process of getting models out into production. So you can speed that process from taking models that you actually built and have them generate value for the business. And then we give you a single pane of glass to see all these models that you have running out in the wild, to see how they're being used, how they're performing versus when you use them, and decide when you want to update or republish those models. So today what I want to talk about is how you can use LLMs for real-world use cases that you may have. So we know that pre-trained models are great. They can save you a lot of the work of having to build these models in-house. But often the use cases that we want to use these models in have some criteria that make a off-the-shelf foundational model not necessarily applicable. First, there's some business context that you care about. An LLM that you find off the shelf, or if you want to use ChatGPT or an existing NVIDIA model, may not know a lot about your business, right? You have proprietary data, maybe based on the products that you have, or different things that your customers do, or other internal data. And a model that you find is not going to know any of that off the bat. There's also specific vocabulary, maybe terminology or concepts that are unique to your products and the industry that you work within. And you're going to want to make sure that a model or a product that you deploy is aware of those things. And finally, you may expect output of that model to be in a specific structure. So maybe you want to use a question and answer template. Maybe you want to summarize certain types of documents. Maybe you're interacting with an API. So making sure that anything that you submit to this LLM comes back in a useful format to you is going to make it 100 times more valuable. There are a few ways that we can customize LLMs to our needs. Here are four of the most common ones. Number one, prompt engineering. This is one that we're probably most familiar with. So if you go use an existing LLM Q&A chatbot today, this is coming up with prompts that are going to get a specific response that you want. So besides just the information inside the prompt, you may decide to tell a model, use this type of experience, act like you are X and Y, and that can help guide the output or the information that model looks like internally to help give the type of response that's going to be most valuable. RAG is another category that's been pretty popular and many of you may have exposure to. What RAG does is indexes contextual information, so this can be company data or other data sets, and builds a vector database, which is a format that can be really efficiently queried and provide information that is relevant to go inside of your prompt. So if I was building a chatbot based on company information and I asked something about one of the products that our company has, what RAG would do is use a vector database of maybe all of our documentation or marketing collateral, be able to go find the information relevant to that product, submit that as part of the prompt to this off-the-shelf LLM. And that's going to give that LLM the context it needs to better answer my question. Full fine-tuning is maybe the most expensive of all these. That entails effectively going through the same training process that LLM originally went through, but you're starting with a model that is already pretty performant, right, in a lot of general use cases. So you would take that same LLM, you feed in specific context-specific data with expected outputs, and you go through a training process until it converges and starts to give you really good results. What we're going to talk about today is parameter-efficient fine-tuning. This gives you all of the benefits of full fine-tuning, or most of the benefits of full fine-tuning, at orders of magnitude less cost, and allows you to actually implement this in a lot of cases where it may otherwise not be justifiable to run full fine-tuning on a model. There are a few different ways to do parameter-efficient fine-tuning. So first is prompt tuning. Prompt tuning is similar to prompt engineering. So when you submit a prompt to a model, instead of manually writing out kind of what you want that prompt to look like, you can generate an embedding through a training process that comes up with what the right information or sequence of tokens is to provide to that model in addition to the user's prompt. A lot of the times these are not necessarily human readable because they're going to be generated by some automated fine-tuning or training process. But a benefit is that you can get better results than you may get with manual prompt engineering. Prefix tuning is similar to prompt tuning, but in this case, those embeddings that we generate are not just added to the initial prompt, they're also going to be added in between each layer of the model. So now you're effectively giving some additional information, not to the degree of fine-tuning where you're changing the actual model, but you're kind of providing additional context that's relevant at each level of the model. P-tuning is, instead of using a static set of embeddings, you have a prompt encoder, which is backed by an LSTM model. And this is used to predict the set of embeddings that you should provide with that prompt. And then you can use this effectively the same way that you would use prompt tuning, except you're getting a more prompt or user prompt specific set of embeddings to append to that. The alternative that I want to talk about today is LoRA, which is low rank adaptation. And what this does is allow you to perform more of a traditional fine-tuning process without a lot of the cost. So you break the matrix or all of the weights that you have to train into a substantially smaller set. And then you're able to actually just do training on that subset of weights. And I'll explain how that works in a minute. So let's dive deeper into how LoRA works under the hood. This is the main figure from the LoRA paper. You can see a reference to that down there. And I want to take 5 minutes because I do think it is possible for all of us to walk out of here understanding really deeply how LoRA works under the hood. And that's going to make it easier for you to understand why it works and when you would want to use it. So let's look first at traditional fine-tuning, because we'll be able to more easily contrast LoRA with that if we understand how the traditional approach works. So traditionally in fine-tuning, you have some foundation model, and you can see the pre-trained weights W on the left. This is everything that you would get. Maybe this is what's inside of an existing model that you pull from NVIDIA. If you use something like Llama, these are the weights that have already been trained. Here, you go through, you have some set of inputs that are more context specific to the type of thing that you want to do. And then you have some set of embeddings or outputs of what you expect. Again, these are going to be context specific for your use case. So in traditional fine tuning, you start with these inputs, you run them forwards through the model, you get some set of embeddings. Through back propagation, which is the same process used to actually train the model in the first place, you feed these embeddings back. And this gives you a delta W. So this is the update that you want to make to the weights of the model that were pre-trained. And as you go through this iteratively, that starts to converge, right? The delta W gets smaller. The model now becomes trained towards the use case that you want to use it for. And when you reach whatever your tolerance is, that's when you can stop. The notable difference in the way that LoRA is implemented is you go through that same process. But the final result you get is not some new set of pre-trained weights W, right? The new trained weights. You actually keep those pre-trained weights in the model, and you add a delta W, and you permanently keep those separate. So through every iteration, you're just updating this delta W, but you never add that back and compress it to your original W. What this allows you to do is exploit some properties around delta W that can make training substantially more efficient. So we're not going to go too deep into linear algebra, so don't let this slide scare you off if you weren't expecting this to be a deep math talk. So all that we need to talk about here is kind of multiplying two smaller matrices to make a big matrix. So delta W is going to be the same size as the original set of weights in that model. So if that's an m by n matrix, which is just the length of how many elements there are in each direction in the matrix, we can get that same size matrix back by multiplying a smaller m by r matrix and an r by n matrix. And the reason why we care about this, and this is not just a completely random factoid, is each of the columns or rows in delta W are not necessarily independent. So from a much smaller set of those columns, we can actually rebuild the entire matrix. This means that it's low rank, and this is what allows us to exploit the fact that with a relatively small r, in some cases as small as 2, we can build a very accurate representation of that delta W, and we have to train substantially less parameters. So now you can kind of see what this looks like for that original figure that's in the paper, right? We have the set of pre-trained weights W on the left. We have A and B, which get multiplied to make the delta W, and that is the approach that's represented here. Concretely, the type of savings that you could see. So let's say you have a 10 billion parameter model, and generalize that into a 100K by 100K matrix. If we use LoRA and break this down into two smaller matrices A and B, instead of having to train a 10 billion parameter matrix, if R is 2, right, we only have to now train 400K parameters. So that's many orders of magnitude less, that's substantially cheaper and faster that we're able to train a model. And that allows us to apply fine-tuning in cases where traditional fine-tuning would be too expensive or limited. So how does NVIDIA help us with this process? So there's 3 things in NVIDIA supplies that can help, and I'll talk a little bit more about each of these. First is NeMo, which is a framework that enables you to go through an entire model training process without having to implement everything from scratch. Second is having pre-built containers and existing templates, basically assets that kickstart you in using NeMo, so you don't have to even come up with all the NeMo code from scratch. You can start even further along the process than that. And finally, having a set of pre-trained models. So in the demo that you're going to see, we use NVIDIA Nemotron, and you can get these models from NVIDIA that are tuned for a variety of different use cases. So you can still fine tune on top of that to be specific to your organization or whatever business need you have. But you're going to be starting from a much better place than a general pre-trained model. So for NVIDIA NeMo, it is an end-to-end platform to develop custom Gen AI models and be able to run and deploy those. NeMo is designed for enterprise development. It is a part of the NVIDIA AI Enterprise software stack. You can see here some of the different components that are available in NeMo, right? So it helps you handle things like actually getting the data exposed to the model, the things about training that we talked about, like applying LoRA, how you have guardrails around deploying this safely, and then also NIM, which helps you package this up and actually get it into production. In the NGC catalog, which is where NVIDIA provides most of their pre-built assets, there's also over 30 optimized foundation models that you can use for different use cases. So let's say you're building a specialized model for code generation or for image conversion, you're able to start with one of the ones that you see here that is closest to your use case. And then the fine tuning is going to be cheaper because you're starting from a significantly better starting point than maybe a general model that wasn't trained specifically for code generation. And how does Domino help? So Domino is an end-to-end platform for AI in the enterprise. We're built on about 10 years of work that we've done to support classic and Gen AI use cases. So including running compute in different locations, being able to put access to data in the hands of data scientists so they can get role-based access control to the data that they need and use the tools that they want to use. And we also have a bunch of Gen AI specific features. So we have the AI Hub, which shows pre-built templates with software and code that you're going to be able to use to kickstart these projects. And we'll see one of those in the demo. And also vector data source connections and fine-tuning wizards like that can also help in different parts of the journey. How we do all of that is that we're a system of record. So Domino is an application that runs in Kubernetes. That means that we can run on all the major clouds. We can run on-prem. We can run across all of those, right? So if you have different needs for different parts of your organization, we can support all of those workflows from a single system of record. We allow you to connect to the data you want to use, the tools you want to use, manage under the hood distributed compute frameworks and things like that allow you to scale the models that you want to build. And then once you've built those models, actually get that all the way through, putting that into production. So both allowing you to put it into production in a bunch of different ways that you can see on the right here, like APIs or different apps that you want, but also track the performance of those models into production, the cost that was associated with building each of those models, so you can make better decisions for each round of models that you put out and really build that organizational capability over time. Now I'm going to pass it over to John so he can show you what this looks like in a hands-on demo.
For this demo, we're going to start here in the Domino UI, which you see in front of us. More specifically, you're looking at the project landing page, which is typically going to be the starting point if you're a data science practitioner. Projects at a high level are essentially boundaries within Domino that allow you to split up your work. A project consists of various files, code, data, workspaces or compute, experiments, and so on. Anything that is relevant to your project is tracked under it. If you were starting from scratch today, you could come here and click on New Project by clicking this button here and specifying the details for your project, and that will give you a blank slate to start from. However, a different way you can start a project is by going to our AI Project Hub, clicking on the templates here below, and that'll allow you to, instead of start from a blank slate, actually start from a pre-built template. You can see in front of us there are a few templates that are available for you to browse through. The one in particular that we'll be using today is the one here called the NVIDIA NeMo fine-tuning using LoRA. When I clicked into that template, you notice the modal here that came up that gives you some key information for this template. You can see information such as the model that will be used. In this template, we'll be actually using the new NVIDIA NeMo model, information about the source code, the hardware, the environment, and the data, and so on. One thing in particular that I want to call out is the source code link here. If I click into the source code here, this will navigate you to the Git repository that actually backs this template. And while this example will run best on Domino Data Lab, and we obviously recommend you use Domino with this template, by all means, if you wanted to come and you see an example of the notebook, you can see that this template is actually public, and so it is accessible to anyone. Going back to our project view, however, if you wanted to actually start use this template, then what you would do here is click the Create Project button, and then you would fill in the details for your project. Creating a project does take a little bit of time as we need to set up some resources, primarily the compute and environment. And so I've already pre-created this project from this template ahead of this demo. So we'll hop over to that project on this tab here. You can see on the left side panel here, before we were in the projects page. We've now gone one level into the hierarchy. And so what you're seeing here are things that are particular to the specific project. Starting in the overview page, one thing you'll see is that in the overview page, the README that was part of the repository is nicely rendered for you here as a starting point for your project. This, as you can see, gives information about how to run the project and the setup instructions. The code that we saw earlier, if we flip over to the code page here, and this will take a little bit of time to render. Once we're in the code page here, you can see that the code that we saw earlier that was part of that Git repository is also included here. I now want to dive into the settings. And I want to call it, you can see here in the settings page that as part of the project, a number of defaults have actually been set. One thing in particular that I actually want to call out is the compute environment. You can see here for this project, an environment called NGC NeMo Framework is being used. And I'm going to spend a little bit of time to dive deeper into this environment concept, as this is kind of the secret sauce that allows you to use Domino together with the NeMo toolkit. To do that, I'm going to click into the Manage Environment tab here. And when I open that, you can see that here, this is the definition for that NGC NeMo Framework environment that you saw earlier. So to give some context, all the executions in Domino run on Kubernetes clusters. And so what an environment simply is a specification for how you want to build the container that will ultimately run on the Kubernetes pods. In this case, the environment, you can see at the top some basic information like the name, description, and visibility, which you can edit. But the first key thing to point out is the environment base. The environment base image is essentially telling us, what is the baseline to create the image from. In this case, you can see we have, in this environment, we are starting from a custom base image. And more specifically, that base image is actually the NeMo container that is actually provided by NVIDIA. To give more insights into what that is, I'm going to flip over to the NeMo tab here. You can see that here we are in the NGC catalog, where for the NeMo framework, NVIDIA has actually provided a built-in container that comes essentially with all the necessary dependencies to run some of the NeMo toolkit examples. So the dependencies that come in these containers include things like PyTorch, things like transformers, Hugging Face repository, and most importantly, the CUDA drivers. You can see that NVIDIA does keep these containers quite up to date with quite regular updates each time they have a change within their NeMo toolkit, or each time one of the major libraries update their versions. You may have noticed earlier that I was using the 24.01.framework image, but I could have chosen any of these if I wanted to, simply by copying the string here and going back to the environment base image and changing that when I create the environment. So the environment base image using NeMo allows us to ensure that the NeMo toolkit and all the code that is related to NeMo will work. But the other thing we also have to ensure is that all the Domino dependencies are also included in this environment. And so in the Docker instructions here, you can see there's a couple extra lines here, which are predefined scripts that will also get executed. And essentially what the scripts do is that it'll check the base image for dependencies that are already in there. It'll cross-reference that with the required dependencies for basic Domino functionality to run, and we'll install the additional packages that are necessary. Lastly, I want to call out the pluggable workspace tools here. These more precisely are essentially IDEs or different applications that you want to have exposed in your container. We'll see more about how this shows up in just a second when I talk about compute. But before I do that, in a nutshell, this is essentially the environments. There are a few things, as you can see, that has to be configured here, but I just want to remind you that this was actually part of the project template. And so as a user, you really don't need to worry about any of these execution scripts or pluggable workspaces. These are simply things that come with the project template. So that's the environment. And now I'd like to go back into the project UI. So we've talked about code and we've talked about the environment. And the last piece that's missing before we can actually dive into the demo is the place where this code and environment actually gets deployed to, and that would be the actual compute. For that, I'd actually like to introduce a concept which we call workspaces. Before diving into workspaces, at a high level, workspaces are essentially an interactive development environment, which you can actually spin up on demand as a data scientist. And this will run on whatever infrastructure that your admin has enabled through the deployment. For this demo, you can see that I already have a workspace that's running. We all know how hard it is to get GPUs these days, and I'm already taking the risk to do a live demo, and so we're not going to risk this even more. But I do want to kind of go into the details about how you may want to configure a workspace if you were to start from scratch on your own. And so if I were starting from scratch and I needed my own workspace, I would start by clicking this Create New Workspace button. And now it pops a modal. You can see where there are a number of options that you can configure for the workspace. The name, of course, you can we'll put something arbitrary for now. The environment, by default, you can see is set to that NGC NeMo Framework environment that we spent some time to dive into earlier. If I wanted to use a different environment, I can also select other environments that are available in the deployment. For the IDE, earlier you saw that large snippet of code on the different IDEs that we added. That essentially translates to the options that get populated here. In this project, since it is a Python-based project, so we have enabled Jupyter Lab and VS Code, but Domino does support a large collection of IDEs, such as RStudio, SAS, and MATLAB, and so on. And so depending on your preferences or the language that you're using, you may want to use, you can actually enable many types of IDEs here. Next thing is the hardware tier. So the hardware tier, in a nutshell, is really a specification of compute size to deploy. If I actually open up this list, you can see a list of hardware tiers that are available. And notice that each hardware tier has a unique number of cores, RAM, and GPU that are available, along with its rough cost and how long it will take to spin up. Another thing you might notice are these little subheaders here, DGX-1 and local. What these actually specify are different data planes that exist in Domino. So more specifically, the DGX-1 here, the hardware tiers under this section, these will actually be hardware tiers that run on an on-prem cluster, which we have access to. We'll actually be using the GPU hardware tier in this data plane for this demo. But the local data plane, for example, if I were to select one of these tiers, these would actually be instances that run in AWS. And so this concept of different data planes becomes really useful in use cases, for example, where perhaps you want to spin up a GPU in AWS, but there's no capacity in AWS, and you happen to have capacity on-prem. And so you can easily switch to the on-prem cluster. Perhaps your organization also allows access to Azure or GCP. Those could also be different data planes, and those could be computes that you can use in scenarios where perhaps other data planes don't have capacity available. And as I mentioned, we'll be using this hardware tier, so we'll just select this for now. The last option here is the volume size. This is essentially the disk space that will be allocated to this workspace. Going on to the next section for the compute cluster, we're not going to actually be using this in the demo, but I do want to call out that Domino does support a number of different types of compute clusters. Spark, Ray, Dask, and MPI are the main ones here. And so if you did have, for example, a large data processing script that runs on Spark, then you could select the Spark option, specify the configs for that Spark cluster, and then you would have something where your Spark code can run on. And lastly, I want to go into this final additional details section. There are a number of things here, but the main thing I want to call out is the data that will be mounted section. So when you're working with these large language models and likely working with large data, it is probably likely that in many scenarios, you don't want to be writing artifacts into the local disk space, and you want instead to write it to somewhere that can be mounted and persisted for a longer duration. For that, we offer a couple of options here. If you have your own NFS storage, for example, in this case, we do, you can actually attach that as an external volume, and then that will actually get mounted to the compute. If you weren't coming with any existing external volume, you can also leverage this concept called datasets, which is really our managed version of a persistent volume, just like a regular external volume. But in this case, it's actually just created for you by default. And so this is just another volume which you can actually write your data to and will be persisted across executions. So those are the settings that you would go through if you were to launch your own workspace. Since we already had one created, I'll just cancel out of this. And we'll jump right into the workspace. So as you can see here, this is what the workspace looks like. For those of you who have used Jupyter Lab, you'll notice that it is basically the exact same experience, and this is done purposely. The only thing different is really kind of the top part here and the side panel, which shows information relevant to the workspace, such as the file changes that have happened. So this would basically be all your Git tracking here, the data that was mounted. In this case, an external data volume was included here. And so if I wanted to create something that would persist across executions, I could write it to this path. And then I can use that in many places. And then this settings showing the environment and the hardware tier, and then the logs. So we'll close out of this now, though, and we'll now focus on the actual fun part, which is the demo. For this demo, I'm going to actually start by running all the cells, as fine-tuning or loading and fine-tuning the model does take some time, so we'll just kind of get ahead of ourselves a little bit. But I'm going to spend some time to go through each cell here one by one. The first section here is for getting the model. So the Nemotron model, which we are using, currently is actually a gated model in Hugging Face. And so if you haven't already done so, you would want to start by going to the Hugging Face page here and requesting access to the model. Since I've already done this ahead of time, you can see that for me, it shows that I've been granted access and I'm able to see the model card and, most importantly, the files that contain the model itself, which you can see is approximately a 17 gigabyte file. So once you have access, then really the first thing you need to do is download that into your environment. We've included some code in here for you to download that model in. If you don't already have one, what you'll need to do is change these two parameters here to your Hugging Face username and your access token. Once you do so, this cell here will download the model in for you. In my case, the model was already downloaded since we didn't want to sit here waiting for 17 gigabytes to download into my environment. Once that's downloaded in, then the next step is to prepare the data set. For this sample, we'll actually be using the Squad dataset. And if I open that up, this stands for the Stanford Question Answering Dataset. And essentially what this is, it's a reading comprehension dataset that consists of a series of questions posed by crowd workers on a set of Wikipedia articles, where the answer to each question is a segment of text that is part of the reading passage. So that's the data set we'll be using. For these first few cells here is really just downloading the data set into your environment. And then the next section is when we process the data sets. NeMo toolkit actually, the NeMo container actually came with a pre-processing script specifically for this data set. And so for this demo, we are going to basically just run that script, and that will prepare us the data into the format that we need. In the next cell, you can see what the prepped data actually looks like. You can see that for each item, there's an input, which consists of the context, which is the text, the question that gets asked, and then the output that corresponds to the right answer to the question. Obviously, in reality, you likely wouldn't be using the squat data set, but you would be using probably your own proprietary data that is likely require much more pre-processing. And so in reality, you'll be spending a decent more time on here. But what this example aims to show is what the format or output format of the data should look like. And that gives you some guidance into how you should process your data. Once my data is processed, then we can go into training. So for training, the first thing we're going to actually do is loading a fine-tuning config. So one of the cool things about the NeMo toolkit is that instead of specifying the different parameters that you may want to use in your training inline in the code, what you can actually do is specify that in a YAML config. So this is the YAML config that we're going to be using for fine-tuning. And as you can see, there's a long list of things that we can configure. But to point out a few things, for example, you can see the number of devices, precision are things that we can change, max epochs, steps, and so on. For this demo, we're mostly going to be using this config as it is. But in reality, you would likely spend some time here updating these parameters, trying different epoch sizes, different batch sizes, different steps, different precisions. And probably do some hyperparameter tuning using this YAML file. But to go back to the notebook here, as you can see, we start by loading in that file. And just to demonstrate an example where perhaps you might actually want to just modify things inline and change the parameters inline, you can just simply change the config file by specifying the parameters here and setting that. In this case, we're just given an example where we're setting the model path. And so when you downloaded the model earlier, if you did want to put the model somewhere in a different data set or a different persistent volume, you can do so and set the path accordingly. This next cell here are distributed training parameters, which we're not going to be worrying about because for this example, we're going to be using just a single GPU. But if you were using multiple GPUs, you may want to configure these parameters. Once we've loaded in the config, then the next step is to really just use that to configure the training. So there's a few things that are happening here. You can see we're creating the container, merging the config, restoring the model from its original path, and most importantly, adding that LoRA adapter that we talked about in the presentation. One thing you notice is that config file that was loaded in, we're essentially just using this throughout this code. And so this, by leveraging the config file, it kind of keeps the code much cleaner and easier to digest. One thing I want to point out, if we scroll to the bottom here, after the model has been loaded in with the LoRA parameters, you notice the number of trainable parameters here is 16.8 million. And that is significantly less than the 8.6 billion total parameters that were actually in the original model. And 8.5 billion of those are actually the non-trainable, non-LoRA parameters. So once I've configured my training, I can also configure my experiment. We're doing here mainly for the purpose of logging checkpoints, which we'll then use later to load and evaluate the model. And then lastly, we can finally train the model using your typical trainer.fit method here. And you can see through the logs here, this is your standard training logs going through multiple epochs and steps and checking the validation loss in the process. You can see at the end, we've basically have created checkpoints that are stored in this path. So with those checkpoints created, then we can now finally, we can load that in for evaluation. On the evaluation side, in a similar fashion to training, we also have a config file that has been specified. In this case, we'll also load that in. And then we'll, in this case, set the paths, primarily the restore from path for the LoRA adapters to the checkpoint that was created during the training. Once we've loaded that evaluation config, then we can then load in that model again. This is pretty similar code of what we saw earlier, but this time just with some inferencing specific functions. One thing to note is that in this example, we are simulating a more practical example where you would likely train the model, store it somewhere, and then pull the model again, pull that model in again in an inferencing server. If I wanted to, I could have also kept the same trainer that was used for training, modified the configs for evaluation, and not have to reload the whole model in like I'm doing here. But in this case, once I've actually loaded in the model, then the next step is loading in the actual data set here. This is your typical data loader where we're gonna basically specify once again, some configs to where the data set is located and the batch size. And then lastly, we'll run the predictions. And so this is taking a little bit longer than expected. So I'm just gonna hop over to a notebook that I had already previously run over here. Scroll to the bottom. You can see it's just the identical notebook that I had ran earlier. And I wanna go straight to the responses here. In this last cell, once the prediction has been run, you can see in the output here that we printed some of the example predictions. So looking at the first one, we have the user giving some context that talks about the Super Bowl. There is a question being asked about which NFL team represented the AFC at Super Bowl 50, and the assistant here is answering with the Denver Broncos. Looking briefly at the text, that seems pretty accurate, given that Denver Broncos here is mentioned as the champion that defeated the NFC champion, the Carolina Panthers. And so that's a quick example of how you can do fine-tuning and then also perform evaluation using LoRA adapters. Obviously, I want to call out that in this case, we are using a fairly simple data set and we weren't doing super long fine-tuning. In reality, you're probably going to be using your own data and you're likely going to have to spend a lot of time processing that data and then also spending a lot of time tuning the parameters in the training process as well. And so that will obviously take much longer, but the goal of this example is to really just kind of give you that starting point so that at least you can get something working quickly and then spend your time on the fun part, which is tweaking parameters and trying to optimize your loss functions. And so that's all I have for this demo. I want to thank you very much for watching this.
Hi, everybody. So hopefully you enjoyed that demo just now from John. John actually had to step away. You may not have noticed because he did such a great job, but John is actually our in-house AI that we use for demoing. So we had some data come from our pipelines last night and he's being offline to be retrained. But he did have time to do this demo first and answer some questions in the chat. So I think there are two questions I see in the chat that were already answered by John. I can add a little on these. So the first one was around industry practices in fine-tuning models for controlled and classified information. And I think what John said there is exactly correct. So for customers that we work with, we work with defense customers. We tell them not to use any other sensitive data with RAG where it's being pushed to some public API. So running smaller models that you're able to run locally and do the inference in your own infrastructure or in a VPC that you control is definitely preferable there. And fine-tuning or using LoRA with something like a 7 billion or 20 billion parameter model can allow you to actually serve a lot of those models really efficiently from your on-prem infrastructure. The other question that I see in here, and if you have more questions, feel free to keep adding in the chat, and I can answer any of those that you may have. The other question is around text classification in a low resource scenario. So typically, what's going to be limiting in this case, right, is trying to get more. So if I'm reading this correctly, Nisreen, is this low resources in terms of the hardware that you have available to train this on? That's what I'm seeing instances as. And assuming that's correct, that mostly will just affect the time scale that your training takes, right? So doing parameter efficient fine tuning like LoRA can help speed up that process, right? You can kind of compress the amount of work that those instances have to do, but you're still going to want to tune that R parameter, right? Maybe you can't go quite as far into the parameter efficiency. You have to meet somewhere in the middle between an R of 1 and doing the full fine tuning. If there's any other questions too, we have about 10 minutes too. I can answer anything that you may have. All right. Well, if not, I'll give everybody 10 minutes back. So thank you all for tuning in, and we hope that you learned a lot about Domino, about NVIDIA NeMo, about LoRA. And if you have any questions that come to you afterwards, please feel free to reach out to us. You can either send us an email. I think we can put maybe in the chat an email address that you'd be able to reach out to. You can also reach out to me or John on LinkedIn, and we can get you routed appropriately or get you an answer. Thank you very much.